Okay, hi guys. We can finally now in this new section 6.4 derivatives of logarithmic functions. We can now talk about the derivative of logarithmic functions since we talked about exponential functions, or at least e to the x. We'll talk about the derivative of b to the x in this section as well, and the integral of it. But like I said, ln and e to the x, they're such special functions that we kind of start off with those. So we might as well just kind of go through the proof of this just so you can see where it comes from. Is the derivative, just right off the bat, the derivative of ln of x is 1 over x. So this is really nice. Okay, and how do we get this? So how do we do this proof? So suppose, right, that ln of x equals something y. So we're going to let y, we don't do many proofs, but this is pretty short, so we'll just do this one. So the proof is, suppose you let y be ln of x, which it is, right? You stick something into this function, you get some output y. Now, remember, because we can turn this into this form, we can say that this is the same thing as e to the y is equal to x. Because remember, in general, if we had log b of x equals y, this meant that if you take the base, raise it to this power, that would be equal to x. And in this case, our base b is the number e, which is like 2.72. Okay, so this is the same as that. This is the equivalent as that. Okay, and now let's take the derivative of both sides. So now, if you take d over dx, key thing here is this with respect to x, of e to the y, this ends up being, you gotta do it to both sides, d dx of just x. Okay. Now, the right hand side is pretty easy. What's the derivative of x? Is just 1. So we get something equals 1. Maybe I should. And then to take this derivative, we need to use the chain rule. Because remember, it says we take the derivative of e to the blank, which is itself. So the derivative of e to anything, that's just going to be itself. So it's going to be e to the y. But now, because of the chain rule, we multiply by the derivative of the thing that we were covering up, which is y. So times d over dx of y. But we write the derivative of y with respect to x. This notationally we write as dy dx. So this is just saying e to the y dy dx is equal to 1. Okay. And then if I come here, that means now, let me just rewrite this. Remember, dy over dx, another way of writing that was y prime, right? Or the derivative. So the derivative, y prime, e to the y times y prime is equal to 1. So now if you multiply both sides by e to the negative y, to cancel things out on this side, because right then you get e to the negative y plus y here, which is just e to the 0, which is 1. So then overall, here now, we're getting y prime is e to the negative y, but e to the negative y is the same as 1 over e to the positive y. Okay? And then what did we define that as? I erased it, but remember that we said that because ln of x equals y, that meant that e to the y equals x. So e to the y is equal to x, and we're done. We see the derivative y prime is equal to 1 over x. Because y is this function. So y prime is the same thing as the derivative of ln, which is that. So we are done. Okay, so this is a very important formula. It's the derivative of ln of x. Okay, very neat. It's going to be very useful. So let's do one little practice with this. So say we want to find y prime if y is equal to the ln of x cubed plus 1. Okay? So because this is not just ln of x, to take its derivative we have to use the chain rule. So what does the chain rule say? It says cover this up and then just take the derivative of ln normally, which is going to be 1 over the thing we covered up now. So it's going to be 1 over the thing we covered up, but the cost, the price you have to pay with the chain rule is always you multiply by the derivative of the thing you covered up. Okay? And then so this derivative here is just 3x squared, right? So we get 3x squared all over x cubed plus 1, and that's our derivative. So that's pretty neat that now we can take the derivative of a lot more things. Things are starting to open up and look nicer for us. Okay. And then let's see, I don't want to belabor the point too much. So maybe one more example, we'll say, is, just to use different notation, is find d dx of ln of sine x. Okay, so find the derivative of this function, and again it's going to be the chain rule. So what does the chain rule say? Again, it says you take the derivative of just ln normally, so it's going to be 1 over blank, the thing I'm covering up. So it's 1 over, because that's x in this case, sine x is like x, so it's 1 over sine x times, again, the price you paid because of the chain rule, is you have to multiply by the derivative of the thing you covered up. So then this becomes 1 over sine x times cosine x, which is cosine x over sine x, right? Because this is technically over imaginary 1. You multiply the numerators, multiply the denominators, you get this. And when the dust clears, it's cotangent. So that's pretty interesting, is the derivative of this ln of sine x is cotangent x. That's pretty cool. Okay. Now, the next thing that we're going to do is, this example will lead us to find out what the integral of 1 over x should be. Because notice, anytime we have a formula like this, if we take the integral of both sides, we're going to get something meaningful, because the integral will cancel out here, and it'll stay there. Okay? So, this is not the exact form yet. We have to do one more thing to make this kind of concrete. So what we're going to do is suppose our function f of x is the ln of the absolute value of x. Okay? And so remember, the absolute value of x was defined like this. It's, the same input comes in if it's positive or 0, but you want to tack on a minus sign if the input was originally negative. So like, why is that? So notice, if you take the absolute value of 3, 3 is like x in this case. So all you want to do is, obviously we know the answer is 3, so we don't want to touch it. But if we take the absolute value of negative 3, meaning we're in this scenario, our input is negative, or it's less than 0, to get the right answer, we need to put a minus sign out in front of it. So now this is minus negative 3, which gives us the answer that we expect is also positive 3. So that's why the absolute value of x is defined this way. And because of that, if we now stick this into ln, so we're sticking this guy into the ln function, that subsequently means that the ln of the absolute value of x is just going to be ln of each of these pieces. So it'll be the ln of x if x is greater than 0. So in this case, we can't include 0, right? Because the ln of 0 or the log in general of 0 doesn't exist. So we can't include that. And also, we can't take the log of a negative number, right? So we have to put this minus sign out in front of it for the same reason, is if now your input is negative, tacking on the minus sign in front of it will make it positive, and that will allow us to take the ln of it, or else you wouldn't be able to again. So this is just making things work. Okay, and now we're going to want to find the derivative of this function. So this means that f prime of x is just going to be, again, you just take the derivative of each of these pieces on their corresponding set of values. We already talked about what the derivative of ln of x is. It's just 1 over x. And then if we take the derivative of this, we use the chain rule, right? So it becomes 1 over, the derivative of this is 1 over what we covered up, so 1 over negative x, times the derivative of the thing we covered up. So this is 1 over negative x times, this is negative 1, which just gives us 1 over x again. So in both cases, actually, you get this. In both cases, the derivative is 1 over x. And so this is not really, this piecewise function, you don't need to write it as a piecewise function anymore, because it's not taking on two different forms. So now you can just compactly write this as, 1 over x if x is not 0. That's the only number we didn't include. So that's pretty interesting. And now because of this, what do we see? So let's summarize this here. To summarize this, what we found out is this. The derivative of the ln of absolute value of x is 1 over x. That's basically what we figured out. As long as x doesn't equal 0, we're good. Which happens for many reasons, right? You can't stick 0 into ln, and you also can't divide by 0, so this inclusion of 0 is very bad in this case. And now we're going to do the same trick that we have done all along, is if now you take the integral of both sides, like we said, FTC says that these cancel, and so you get that the ln of the absolute value of x plus c again is equal to the integral 1 over x dx. And this is a new integral that we established. So when I put this on the exam, I remember, and I accidentally put this on the exam, this was the integral that we hadn't talked about yet, that you needed to be able to do the problem. So my bad on that. But now you know how to do it. So the integral of 1 over x is this. And notice that now this fills in the power rule, because remember, with the power rule we said the integral of x to the n was 1 over n plus 1, x to the n plus 1, as long as n did not equal negative 1. But this is the case when n equals negative 1, right? Because x to the negative 1 is 1 over x. So when n is negative 1, aka we're in the 1 over x scenario, we also do know how to take the integral now. And it turns out to be ln of absolute value of x. So that's also a very distinguishing thing. For all other powers, the integral gives you some other power function. But now you get the natural log, so wow, that's kind of crazy. That's a little different. And so yeah, again, you can start to see how ln and e to the x, these are just some really, really crazy functions that just have amazing properties. Okay. So then let's do this example. I'll just recopy this, put this down somewhere just so we remember. It doesn't look quite like the absolute value. Okay, so this is the thing that we want to use in these problems. So say it asks us to find the integral of x over x squared plus 1. Okay. Now again, because there's a division of functions here, that's something that we haven't talked about, and actually there's no real rule to deal with that. And so the only technique we know is use substitution, so you might as well try it. And then if you sit there and you think about this for a second, you can see that if you make u x squared plus 1, that would mean that du is 2x dx, right? You just take the derivative of this, tack on dx. And that would mean that du divided by 2x is what you want to replace dx with. Okay? So then now you have the integral of x over u, right? This is what u is. And then dx gets replaced with du over 2x. Okay, and then very nicely, surprise, surprise, the x cancels. And so we're just left with a division by 2, du divided by 2, which is the same thing as multiplying by 1/2. So this is the same as 1/2. Remember, you can pull out constants into and out of the integral. 1/2 integral of 1 over u du. And this is exactly this, except these are u's, but it's the same thing. So this is 1/2 ln of the absolute value of u. And you don't necessarily have to write these parentheses. It's pretty well understood that if you just write it like this, that's what it means. So ln of absolute value of u plus c, and then once you substitute back for u, this is 1/2 ln of the absolute value of x squared plus 1 plus c. But then notice that if you take any number and you square it, it's positive, and then if you add that to 1, it's still positive, meaning that the absolute value of a positive number is just itself. You don't have to tack on that minus sign. Like, had this been negative, you'd have to tack on the minus sign in order to drop the absolute value symbol. But it's not, so you can just drop it without any care. So this is 1/2 ln of x squared plus 1 plus c. If this doesn't make sense, feel free to ask me in class. Either one of these are acceptable, though. I mean, it's just to be extra cool, going from here to here, they're the same thing, though. You don't really have to do it. Oh, and yes, you can simplify this even more, but we're just gonna stop there. We'll stop there, okay. Okay, and then we should also do a definite integral as well. So just a lot of examples now using this new integral that we have. Integral from now 1 to e of ln x over x dx, okay? Now this one may seem kind of weird at first, but again, the right choice of u will get you there. So again, we're going to use u substitution. I told you it's important. So when we do u substitution, we're going to let u be the ln of x, okay? And so remember that when we do this, we need to find u limits of integration. So u, if you stick 1 into this, you get the ln of 1, which is 0. Remember, we said log base b of 1, no matter the base, is 0. So in our particular case of e, where the base is e, aka ln, this is 0. And then when you stick e in this guy, you get 1. Because again, remember we said log b of b was equal to 1. So if you have log e of e, which we just write as ln of e, that equals 1. Okay, so these are our new limits of integration. 0 and 1. And then now we need to figure out, you know, the things that we normally find out as well. Is what is du? Du is the derivative of this, which is 1 over x dx. And so when you multiply both sides by x, you get that x du, x du is dx. So this is what we replace dx with. Okay, when we do that with the new limits of integration, we go from, so when we stuck this in, we got 0. When we stuck that in, we got 1. And then ln of x was u, and then x stays. But now the new dx is x du, and look how nice that works out. Because now these cancel, which is exactly what we wanted. So now we're just left with a much more boring looking thing, but that's good. Boring is good. It means you can do it. So it's just 0 to 1 of u du, which again, remember, is 1/2 u squared, evaluated from 0 to 1. Remember, we do not have to substitute back for u because we found new limits of integration. These are the limits that correspond to u, so no back substitution required. And so this will just be 1/2 1 squared minus 1/2 0 squared, which is just 1/2. So that's pretty neat. The area under this graph is 1/2 from 1 to e. So that's kind of cool. Okay. Okay, and then yeah, we're just gonna keep cranking out integrals and things like that, because it's good to see get this practice. Okay, and then now let's say we take the integral of tangent x. Okay, so this is something that we did not know how to do. This is not one of those nice integrals that we knew from a long time ago. So the first step is to rewrite this as sine x over cosine x. And then at this stage, we can do a u substitution. So, of course, you either have the choice sine or cosine. And because, you know, I've done this 1,000 times, I know that cosine should be the right choice. So we'll see why in a second. So if you let u be cosine x, that means that du will be negative sine x dx. And so du divided by negative sine x is dx. And this looks like OLU. Let me connect this. Du, there we go. Okay, so then the new integral is now sine x. This was u, and this gets replaced with du over negative sine x. Oh, and very nicely, these cancel out. So all that's left is this floating minus sign, which will just come out in front, because it's like -1, right? A minus sign is just multiplying by -1, so you just pull it out in front. So this is now negative integral of 1 over u du. And again, we know what this is. It's the ln of the absolute value of u. So this is negative ln the absolute value of u plus c. And then what was u originally? It was cosine, which is negative ln of the absolute value cosine x plus c. And then we can be done here, but there's some more tricks that we can do here. Is remember the power rule said that, I'll write it in terms of ln, but this could be any log base, is that ln of something raised to the p power, same thing as p times ln of x. And in this case, p is negative 1. That minus sign is like a negative 1. So what this means is that this is a negative 1, and that's just a minus sign. It means this minus sign, you can pull it into the exponent. This minus 1 goes to the exponent. So really this is the ln of the absolute value of cosine x raised to the negative 1 power. So again, x in math just means something, any expression. In this case, it turned out to be cosine x. It could be m squared over 14 plus 9 plus a taco. You know, it could be anything. It just happened to be cosine x in this case. And then the plus c here. And then when you raise something to the negative 1 power, like we said, it's the same as just taking that same thing and raising it to the positive power, but the reciprocal. But raising cosine x to the first power is just cosine x, right? So this is just 1 over cosine x. And we know 1 over cosine x is more formally known as secant x. So this is ln of secant x plus c. And now we have a really cool formula. Is that the integral of tangent is the ln of secant x plus c. So that's pretty cool. That's a new formula. So before we had like the integral of sine and cosine, but there wasn't one for just bare tangent. And now we have one. So that's, and it's a little more complicated, but you know, it is what it is. Okay. And now, I won't go through the derivation, but if you just use the change of base formula, we can figure out what the derivative. So we have the derivative. We know the one for e to the x was just e to the x. But what is the derivative of an arbitrary base? So it turns out to be, oh sorry, we're not doing that one yet. We're doing the one for log. So we're saying if you take the derivative of ln x, we know that's 1 over x. But what is the derivative of an arbitrary base? Log b. So in this case, the base is e. What if it's just an arbitrary base b? So it turns out to be not too far away. It's still 1 over x, but downstairs here, you multiply by the log of the base, or the ln of the base. So sorry, when I say log sometimes, I've been trained to equate that with ln, so I don't mean to mix those up, because I know that it's not standard. Only math people do this. So long story short is this though. It's the derivative of an arbitrary base log now is just 1 over x, so same thing, but you pick up this extra number. This is just going to be some number. So it could be like 4x or 5x or 6.9278x. Just a small change, but it's still the same form. And then now, again, if you apply similar reasoning that we did earlier and do some more math and whatnot. Again, I won't kill you with the derivation. Is if you take the derivative of now b to the x instead of e to the x, what is the difference? So it's again going to be in the same form. It's going to be b to the x. So had this been e, we would be done, because e to the x is just e to the x. But if it's any other base, you multiply it by the ln of the base. And notice that this works out perfectly when the base is e, because according to this, if you have e to the x, this would be e to the x ln of e, but ln of e is just 1. So you get e to the x times 1, which is itself. And so, in the case where the base is the number e, then it works out the same. So it's just a small trade-off, not too bad. And so this is why, again, ln of x is kind of the more natural log function to deal with. You don't get these annoying factors here when you do use e as your base, aka use natural log. And yeah, when you're using e to the x or ln of x, then you don't get these annoying factors here. But I mean, it's a number, it's a constant number, doesn't matter too much. So these are some nice rules that we established. Okay. And then last but not least is, if we have these derivatives, can you get integrals out of this? And the answer is yes. So again, it's like the same idea as if you integrate both sides, right? It cancels out here. So you would just get this thing plus c, and then you would move it over, this is just a little bit of algebra, so I'll just not really do it. So long story short is the integral of b to the x, instead of just having e to the x, it's the same idea. Is it's going to be now, it'll be b to the x over the ln of the base plus c. So again, just small differences. Small differences here. And the same idea is the integral of log b. So if you use an arbitrary base, what is that going to be? I think, does the book even talk about this? I'm not sure. Yeah, we might not need to talk about this. Okay, forget I mentioned it. Yeah, we're not going to even deal with it. So, no need to talk about it. Okay. So, okay, now the thing that we can see is, yes, you can use another base, but why not just use e as the base? Because it makes everything easier. So, we're just going to stick with that mantra that base e is just the best base ever. It makes life a little easier. Okay. So next, we can do one example maybe. Yeah, maybe this will help solidify things. So say you want the integral from 0 to 5 of 2 to the x dx. Okay, remember the formula we're using is this. Okay, this is the formula that we're going to be using. So in this case, our base is 2. So the integral is 2 to the x divided by the ln of 2. That's what b is in this case. And we evaluate this from 0 to 5. So this will be 2 to the 5 over ln of 2 minus 2 to the 0 over ln of 2. And then so that's just 32 over ln of 2 minus 1 over ln of 2, which, because they have the same denominator, you can just subtract these. So you get 31 over ln of 2. And that's it. Not too bad. Final answer. Okay, so hopefully that helps kind of solidify like what I mean by, oh, if you use something other than E as the base. Okay, and then now we can get to a very useful and interesting process called logarithmic differentiation. It sounds cool, so if you like say it to somebody, they're gonna be like, wow, you're super smart. So logarithmic differentiation. I suck at spelling, so I just try and spell it out in my head. Okay, so the easiest way to learn it is to let's just do an example, and then you could see the process. Okay, so suppose we wanted to find, suppose you want to find, so this is the function. Say this is the function and you want y prime. The derivative of this function. Okay. Now there's nothing stopping us from, using the quotient rule and the product rule and things like that. But we can make things a little easier if we use logarithmic differentiation. Because this thing will look like a monstrosity if we just try and use the quotient rule. Because to use the quotient rule, we'll have to take the derivative of this, and that requires the product rule, so it's going to be messy. So what we do is step one is if you do have y equals something, you can easily take the ln of both sides. So you take the ln of both sides. And actually this process is used in statistics to find, taking the ln of a complicated function can make it look nicer. And you use this in statistics to find something called like the maximum likelihood estimator, which has a lot of properties, and it's very useful for like doing things in like the realms of like computer science or statistics and things like that. So again, this is not it's not just this random thing. It looks kind of random, but it is useful. Okay, so we have this. So all we did is take the ln of both sides. Nothing wrong with that. So the reason why this is so nice is the left-hand side, big whoop, who cares what happened, you just get the ln of y. That's not much different. But the right-hand side, we can use a property of the logarithm to make this a lot simpler. Remember, if you have the ln of x over y, that's like the ln of x minus the ln of y. Or any base. If this was log base b, you can replace those with that log base b. So in this case, the top is x, the bottom is y. So this breaks up into the ln of x to the 3/4 root x squared plus 1 minus the ln of 3x plus 2 raised to the 5th power. Okay. And now we can actually use more properties of the logarithm to make this even easier. So remember, if you had the ln of x times y, that was the ln of x plus the ln of y. So this is like x in this case, and this is like y. So this actually means that the ln of y is the ln of x to the 3/4 plus the ln, and instead of writing the square root of x squared plus 1, I'm going to write x squared plus 1 to the 1/2, which will become apparent why I'm doing this in a second. And in a second is now, because remember the power rule says if you have the ln of something raised to a power, that power can float out in front. So this is like 5 times the ln of 3x plus 5. And because of that, these powers will do the same. So we have ln of y is 3/4 ln x plus 1/2 ln x squared plus 1 minus 5 ln. Pretty neat, huh? That's pretty cool. Okay. And then now we're ready to take the derivative. So now we take d over dx, because that's our variable. You take d over dx on both sides. And then maybe just, yeah, you take d over dx of ln of y, d over dx of this guy. And again, this is like you're taking the derivative of all of this. The derivative of this entire function here. Okay? Now the left side, to take the derivative, we need to use the chain rule basically many times, left and right side. So the derivative of ln, remember, is 1 over the thing that I'm covering up, which is y. So this is 1 over y times now the derivative of the thing that I covered up. But the derivative d over dx of y, we wrote that as dy over dx. That was just the notation. And then another notation is we wrote dy over dx. That was the same as y prime. So this is 1 over y times y prime. And look, the thing that we were looking for, y prime, magically popped out of this. So y prime, we'll be able to isolate for y prime after we multiply by y. Okay, so now let's take these derivatives. So remember, you can just take the derivative of each piece and add them together. That's the sum rule of the derivative. So this is 3/4 times 1 over x, derivative of that, plus 1/2 again, times 1 over x squared plus 1, but you have to multiply by the derivative of that because of the chain rule. And then minus 5 times 1 over this guy times now the derivative of that. Okay? So then again, this is, you can write this as y prime over y if you'd like. And now this is 3 over 4x if you'd like. That's one way to do it. Plus, this derivative is 2x, right? So you'll get 2x in the numerator and then 2 times x squared plus 1 downstairs. And then minus, and then this derivative here is just 3. So you get the 5 times 3, so that's 15 up top, and then 3x plus 5 down here. Okay, and this looks pretty crazy. So then if you multiply both sides now by y, multiply this by y, it cancels out, multiply this whole thing by y, what you get is exactly this, is now that y prime is equal to y times this. And y was just our original function. So now we have the derivative, y prime. So the original function was, so y is x to the 3/4 root x squared plus 1 over 3x plus 5 raised to the 5th power. Sorry, 3x plus 2. Now, have I been copying that wrong this whole time? So sorry, this should be 3x plus 2. It doesn't change anything. Fortunately, that doesn't change anything. And then, oh, one thing I also didn't notice, this 2 and that 2 cancel. So these just kind of go. Okay, so what we have now is, this was y is all of this, and that multiplies this entire quantity. 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. But that's our final answer. This is the derivative of the function we started with. It's crazy. So yeah, it's a very complicated looking thing, but it's still easier and more manageable than had we just like tried to brute force use the quotient rule and stuff like that. So now you can kind of see the process. So the first step is we took the ln of both sides. Then we took the derivative. And then invariably when you have the ln, because you always have ln of y equals something, then you take the derivative of both sides, and that'll turn into y prime over y equals the derivative of that junk. Remember, we got y prime over y in our case. See, look right here. And then you just multiply both sides by y to solve for y prime. So that's basically what logarithmic differentiation is, that process. Okay, and maybe let's do one more example. A little less lengthy now, thankfully. But still very interesting. This function is wild. So let's say y is x to the root x. So now both the base and the exponent are variables. It's a very, very crazy function. Okay? But we can still find y prime through logarithmic differentiation. So again, what do? Is step one is you take the ln of both sides. So you take the ln of y, and that's the ln now of x to the root x. And you might be like, why is this helpful? Well, notice that this doesn't change anything, ln of y here, but again, because of the power law, this exponent comes out in front. So this is root x times the ln of x. And now to take this derivative, you just need the product rule. Very nice. So again, the second step is now to take the derivative of both sides. You take the derivative of both sides. And then, like we said, for the left side, you always get the same thing. Because what is the derivative of ln of anything? It's 1 over that thing. So 1 over y times the derivative of the thing we covered up. But again, notationally, when we took the derivative of y, we wrote that as dy over dx, which we also wrote as y prime, which, you know, when you multiply these, is y prime over y. Y prime over y now is going to be equal to, and I'll have to come down here. And take this derivative, we use the product rule, and to make our lives easier, you can write this as x to the 1/2. So the derivative of the first function is 1/2 x to the minus 1/2, then times the second one, and then plus the original the first function, times the derivative of ln is 1 over x. That's the product rule here. Okay, and so now you get a little bit of simplification, but not much. So this x to the 1/2 is like over 1 times 1 over x. This is like to the first power, right? So this is really like x to the 1/2 minus 1, which is x to the minus 1/2. And then we can go ahead and multiply y on both sides. So you get y prime is y times 1/2 x to the minus 1/2 ln x plus x to the minus 1/2. And what was y? It was the original function. It was x to the root x, and then times this. Which again, you can simplify this more, but it is what it is. And it's what it is. You can do more, but this is fine. Okay, so you can see how implicit differentiation allowed us to take a derivative of something that we could not do before. We basically could not do this, so that's pretty nice. That's pretty cool. Did I say implicit? If I said implicit, I meant logarithmic, sorry. Okay, so that's a nice example there. And we have about 12 minutes left, so I might as well start on the new section. So we're going to skip 6.5. I believe we skipped 6.5. Let me just make sure. And we jump to 6.6, if I'm not mistaken. Yes, 6.5 is a more application, but we're going to jump straight into 6.6, which now we're going to talk about inverse trigonometric functions. So we have, I know that you've talked about this before in a trig course, but now we're going to do calculus on it basically. And just for the sake of review, we can talk about where like maybe sine inverse comes from. So if you remember what the graph of sine, let's just look at it from negative 2 pi to positive 2 pi, for example. Maybe. So it's 0 at these numbers, and then let's just pick out the interesting points. and then it bounces between 1 and -1. So at the origin it's 0, then it hits 1, -1 here. So it looks like this. And then again, because it's an odd function, we know that the rest of the behavior is like that. So, you know, even between -2 pi and 2 pi, this function is very hopelessly not one-to-one. Look how badly it fails the horizontal line test. Okay? So, remember, what do we do is, the inverse function doesn't have to exist on a particular domain. If you can find a domain where the function is one-to-one on, which we saw this in 6.1, then you can find its inverse. And the domain that we're going to focus on is actually this one. This is drawn a little poorly, sorry. At -pi/2, it hits -1, and then there we go. Let me just align this a little better. There we go. -pi/2. So notice that between -pi/2 and then up to pi/2, the sine function hits all of the values that it normally does. It hits -1, it hits 1, and all the numbers between, and it's one-to-one on here. If I draw any vertical line on this red piece, it doesn't touch the function more than once. And so that's exactly the way we're going to define the sine inverse function. So sine inverse x, the inverse of sine, is defined on -pi/2 to +pi/2. So, and then maybe, so what I'm saying is, if you look at sine x, this may be a little ambiguous. So what we're saying is sine x on the domain -pi/2 to pi/2. So this is the domain that we're going to assign here. And so on this domain, it has range -1 to 1. Right? On this domain, -pi/2 to pi/2, it hits all the numbers between -1 and 1. And so what do we say about the inverse function? Is it flip-flops the domain and the range. So then sine inverse x has domain -1 to 1. So you stick in, it can take in numbers between -1 and 1. And it has range -pi/2 to +pi/2. So it spits out a number in this interval. And now if we apply kind of like the meaning of sine or cosine or any of the trig functions to how we originally talked about them, they you can think of their input x as an angle, right? And their output was like a length, or technically the ratio of a length, right? If you had an angle x here, and this length was a, or this is a, b, and c, sine x was b divided by c. So it's the ratio of lengths. And so like -1 to 1 in a sense is like a length, a displacement is a better word, because it could be a negative thing, because, you know, say you were in the fourth quadrant and a triangle looked like this, then this length is technically negative. It's a displacement. So the inputs were angles and the outputs were lengths. So for the inverse trig functions, it's like the opposite. Now the input is a length and the output is an angle. So maybe let's see how we compute this guy, and that'll really solidify things for us. But again, we have the same relationship that we always have for any function and its inverse, is that if sine of x equals y, this implies, or this would imply that sine inverse y equals x, or if this is true, it backwardly implies this. It also implies that. Okay, and also we have the the cancellation properties as usual. So sine of sine inverse of x is x, and cosine inverse. Oh, sorry, I didn't mean to switch to cosine. It's valid for cosine too, but what I meant is sine inverse of sine x is also x. So these are the cancellation properties, but we see this all the time. Or cancellation equations, one of those. Okay, so say you want to find sine inverse of 1/2. Okay. And we're going to kind of do this the same way that we did with the log function. So that equals some number y, right? And remember, we said that if sine inverse, or we call it x, if sine inverse of y equals x, that meant that sine of x equals y. So from this statement, we know that sine of x should be equal to 1/2. Now again, let me label these based off what they are. This is a length. This is an angle. You don't have to think of it like this, but this helps build an intuition. So now this is an angle. So you're saying sine of what angle is 1/2? Now there's an infinite amount of angles that satisfy this, right? Many, many angles have a sine of 1/2. But notice the range is this. So it has to be an angle that falls between these guys. Because this is the input, the output of it is x, meaning this is a value in the range of sine inverse. So it has to fall between these two. And when you think about it, then the answer is going to be pi over 6. This implies that x is pi over 6 or 30 degrees. So that's that's the answer. So long story short is sine inverse of 1/2 is pi over 6. But for reasons that deal with units and stuff like that, very rarely do we use degrees in calculus. So we're going to stick with radians. So this would be like the answer. So it's kind of asking the opposite question, right? Normally, if you say sine of pi over 6, the question you're trying to answer is this equals whatever number. It's the number that if this angle is pi over 6, what's the ratio of this length to that length is the answer to that. Now it's saying if the ratio is 1/2, what was the angle that it had to be? It's pi over 6. So it's just the reverse question. And that's basically all. It's basically what trig functions and inverse trig functions are doing. Okay, and so I think this is a good stopping point. Make you guys a little think about the inverse trig functions, and then we'll talk about the other ones like cosine inverse and tangent inverse and stuff, and then their derivatives and things like that. Okay, see you guys later.